The hook for today may seem vacuous, but it's actually quite rich. Why does it hurt less to fall on soft things like pillows instead of hard things like rocks? And you would say, well, it hurts less because they're soft. And soft means hurts less, but that's not true. Why do soft things hurt less when you fall on them? To get at that, we first are going to land on the moon. A nice, soft, pillowy landing on the moon. That here's a rocket ship with its pilot peeking out at you, and this rocket ship has the feature that you can turn on the rockets or you can turn them off. But you cannot adjust how strong the rockets are. So that this person, oops, you're supposed to be separate. It's not. Okay, so imagine that this rocket is coming down and approaching the surface of the moon, and all you can do is either have the rocket firing or not have the rocket firing. You can't make the rocket fire with more or less force. So what else do you have control over so that you can land softly on the moon? And the answer is time. I really wish this was free, but it's not. The answer is how long you leave the rocket on for. That as long as the rocket, we'll draw some flames at least, as long as the rocket is on, pushing trash down, the trash that gets pushed down pushes the rocket up, and so it slows the rocket's fall. But if you push up for too short a time, then you won't take away enough of the downward velocity of this rocket and you'll crash into the moon. But if you push down for too long a time, if you leave the rocket on for too long, then the engines will push and take away the downward velocity of the rocket until the rocket stops falling, and if you continue to push at that point, then the rocket ship will end shooting up. So if you leave the rocket on for too long, you'll fire back into space. If you leave the rocket on for too short, then you won't slow down enough and you'll crash in. If you leave the rocket on for just the right amount of time, then it will reduce your velocity to a very low value, and you can land safely. And I have a little video of that you get to see when you come to class. But the point being that time is an important factor as regards force and slowing down. Here you have the product of force and time, and now it's just time times something, and I would like you to replace F by an equivalent thing that evidently has an M in it. Whatever was inside of here is now becomes M times something divided by time. And what's mysteriously here? Well, the times go, and so you're just left with that mystery thing. And then that's equal to the change in what? And you fill in that table, and the expectation is that you will have found this here to be the change in momentum. This quantity, force times time, is defined to be impulse. The force times how long it acts for. Exactly that rocket. Its symbol is a capital J, and its units, well, just look here. But what we found in this little exercise was that impulse is also equal to the change in momentum. And that's what we were trying to accomplish with the rocket ship. We were trying to get rid of its downwards momentum and bring it down to 0. and that's going to be the force times the time over which it acts determines how much the impulse, the momentum, gets reduced by. Please note the definition of impulse is force times time, but it is also true, although not the definition, that the change in momentum is equal to impulse. And this provides an alternative set of units for impulse. You got units from force times time, but there would also be units that would come from this statement. So, back to the pillows. Why soft instead of hard? And we need to be very clear that whether it is pillows that stop you or rocks that stop you, they're both going to take away all of your momentum. So it's the same change in momentum, but the change in momentum is equal to impulse, which is defined as force times time. And so if the time got bigger, while the change in momentum was the same, if the time got bigger, which is the case with soft things, you finish it. Somebody's throwing a punch at your face. There is no way you can dodge it. It's going to hit you. You are going to take away all of that fist's momentum. Your face is going to stop it. But should you lean into it, stand perfectly still, stand your ground, or roll with the punch? Again, you have the situation that it's the same change in momentum no matter what you do. You're going to stop the punch. Which should you do? Let me also point out to you that this product of force and time, well, if you graph force versus time, then the product of force and time is area. So this area represents the impulse, or if you like, the change in momentum. So if the area here was the same as the area here, you can see that when you make the time small, to get the same impulse, the force has to be larger. When the time becomes larger, the same impulse is accomplished with a smaller force. This is different. Don't turn off your brains. You hit a ball with a bat or club. What's the advantage of follow-through? One of the advantages of follow-through is it improves your form during the hitting. But aside from that, what is the advantage of follow-through? And please note, in this case, we are not saying it is the same change in momentum. What we're saying is it is the same force. So if you extend the time over which that same force acts, what does that do? Graphically, it would look like this: the same force, but for greater time. What does that mean? Some more problems just to keep our brains working. The same force asks for the same distance on lighter and heavier boxes, which ends up with more kinetic energy. And I'm going to answer this question, so you may want to stop it so that you can take the pride in answering it yourself. That the same force acting through the same distance, force dot distance, means the same work. Energy transformed, so the same change in kinetic energy either way. New problem. If the same force acts for the same time, not the same distance, but the same time, on lighter and heavier boxes, which ends up with more momentum. And again, stop the show if you want pride of ownership in your answer. That the same force for the same time means the same impulse. And so again, boring, same answer. It's going to be the same for both. Here is something that is sometimes marketed as Newton's cradle. I call it a clicker. It is actually a toy, a model, a thing that was created back in the time of Newton. And there was a question, how does it work? Because the wonderful thing is, if you let this one ball go, it comes down here and strikes, and exactly one ball goes off on the other side. If instead you have two balls and you let them go and they come down and strike, exactly two will go off on the other side. And the question is, how does that work? It's mesmerizing to see exactly the same number of balls leaving on the other side as you drop down here. It needed an answer, and this was presented to the Royal Society during the time when Newton was a member of the Royal Society, and Newton did not solve this problem. So you can outdo Newton by solving the problem. That the first response we have is its conservation of momentum, that one ball comes in, hits a stationary ball, and that stationary ball takes off and the ball that hit it stops. And if you were assigned mass and velocity of 2 and the other one had a mass of 2, then you can see that the initial momentum was 4 and the final momentum here is 4 with only the one ball moving. So it would be a conservation of momentum. But I point out to you that momentum is also conserved if both of them go off with half the original velocity. So if they were to travel off together, that would conserve momentum. Or if the one that came in were to bounce backwards at the same velocity it came in at, and the one that was hit went off at twice the original velocity, this would be minus 4 plus 8, it would still be a conservation of momentum. And there are infinitely many other ways to conserve momentum. But this is the only one that happens. So why? And if you want some time to outdo Newton, you can go ahead. Otherwise, I'm going to start pulling these windows away. There was a guy named Huygens. I'll write his name. Huygens, who was a contemporary of Newton's. And he got many things right. And he got the answer to this question right. Some things that he got right, Newton had an opinion on, and Newton was wrong. Huygens, he's a very, very important physicist. You've probably never heard of him, and the reason is because we seem to only celebrate the English in our culture, and we ignore this Dutchman who was a contemporary of Newton's, and there's a great deal of pride in Newton among English speakers, and so we don't like people who competed with him. At any rate, what Huygens said is, the only way to explain this unique choice, when there are so many different ways to conserve momentum, is if something else must also be being conserved. Some other condition has to be met. And what Huygens proposed was that we take, in addition to mass times velocity, we take mass times velocity squared, which would be 2 times 2 squared. That's 8. This one has no velocity, so there's no contribution. And over here, if you take 2 times 2 squared, again you get an 8. So both mv and mv squared are being conserved, whereas if you do it here, you've got 2 times 1 squared plus 2 times 1 squared, and that comes out to be 4. So mv squared is not conserved in this scenario. Here you've got 2 times negative 4 squared, there's your 8, and 2 times 16, that's 32, that's a total of 40. So mv squared is not being conserved. And if those two things are conserved, mv and mv squared, then we have the this is the only way to meet those conditions. Nowadays we know mv squared in a slightly different form, and perhaps you can anticipate this. Instead, we put a 1/2 out front. And you recognize it as kinetic energy. And so today's explanation of this would be that these are very hard steel balls, so the collision is perfectly elastic. All the energy of motion that is there before is still there as energy of motion at the end, almost none becoming heat, and so kinetic energy is conserved as well as momentum. Momentum conserved because it's only internal forces acting. And thus, here you are again, when somebody tells you that you're going to have an elastic collision, then you know that kinetic energy will be conserved. If they tell you that they're having a collision, you know that momentum is conserved because there are only internal forces acting in a collision. If they say it is an inelastic collision, that is, they stick together, then there's only going to be one velocity afterwards. And so this one equation, momentum being conserved in an inelastic collision, is sufficient to find out what this final velocity will be, since these two will have the same final velocity. They're stuck together. But if it's an inelastic collision so that they bounce apart and you have two objects, we can still do the problem because we have one equation which is generated from the conservation of kinetic energy and a second equation which is generated from the conservation of momentum with the same two unknowns. And so you can solve these two simultaneously and get a solution, and I'm going to show you that. Here is a problem typical of the sort of problem you will be given. They give you the masses and the velocities, what we call the initial conditions. And then you say, okay, well, this is a collision, so I know that momentum is conserved. There are no external forces, only those internal forces of m1 pushes m2 and m2 pushes m1. And also, if they say it is an elastic collision, then I would also know that kinetic energy was conserved. And so you have this equation with mv's and this equation with 1/2 mv squareds. I would start with the linear equation, first degree equation, and into that I would put the values that they gave me for the initial mass and velocity, and the final mass stays the same. There you go, two unknowns. But I would, staying here in the linear case, I would solve for one variable, v2, in terms of v1 in terms of v2. Then come over here and again put in the values that they gave you, and where I put in a 2 for the mass, but I multiplied it by 1/2, so I wrote a 1 there, and so on across. And then take this value for mv1 that you got from the momentum equation and put it in for v1 in this equation. And you're going to have to trust me that 16 and 3 times 16 and 12 is equal to 28. And here for v1 I have put in the value, the 10 minus 3v2. Then you would FOIL this. This is actually kind of fun because it works. So you FOIL this one, 10 times 10 and 10 times minus 3 plus 10 times minus 3 plus minus 3 times minus 3. Don't forget this one here. Then you make it homogeneous, that is, you make it equal to 0. Subtract the 28 from both sides of the equation, so 100 becomes 72, and the 60v2, and then I'm going to add the 9v2 squared to the 3v2 squared to get 12v2. This can be factored, and it can always be factored very nicely. If you'd like, you can use your quadratic formula to solve this, but it's kind of fun to do it without the quadratic formula. I would pull out that common factor of 12 from all of them, and that leaves you with 6 minus 5v2 is equal to v2 squared, which factors nicely as v2 minus 2 and v2 minus 3, which means your solutions are that v2 is either equal to 2 or equal to 3. But please notice, they told you that v2 is equal to 2 before the collision. So this second answer must be what v2 is doing after the collision. That is, there are two conditions under which the momentum and the kinetic energy are the same. Before the collision, there was a certain momentum and kinetic energy, and after the collision, the same momentum and kinetic energy. So it's a nice check. When you factor these, one of your solutions should be the initial value. Then you take these and put them back into this equation. If you put a 2 in here, it's 10 minus 6. v1 is equal to 4, but that was the initial velocity. And if you put the 3 in, you get a 1. So there is the answer. There are the final velocities after an elastic collision. If instead the problem had been that the collision was inelastic, then again this adds up to 20. But notice, the 2v1 plus 6v2, those are stuck together if it's inelastic, so I only have one velocity. So I only need one equation. It's very easy to solve that for v. So there's the final velocity of both of the balls if it's an inelastic collision, and here are the final velocities of the two balls if it is an elastic collision. Please try your hand at it. Here is another problem. If you're doing an elastic collision, you will have the momentum equation and the kinetic energy equation. If it is inelastic, then you do not have kinetic energy being conserved, but you don't need it. That if it's inelastic, these two velocities would be the same, and you only need one equation to find out what that velocity is. We will not do this problem, but I want to point out the intricacies of such a problem. What you have is this ball coming along at 10, this ball is sitting there not doing anything, not even rolling with the punch. And then after the collision, the 6 is going off this way at some velocity, and the 4 is going off this way at some velocity, and I would like to know what those two velocities are. Both their magnitude and direction. So I'm going to need to talk about the direction and how big that vector is, and the direction and how big this vector is. Now, as we have seen before, in this two-dimensional arena, we are going to have both the horizontal momentum being conserved. This 4 times 10 plus 6 times 0 was before, and afterwards it's going to be 6 times v2 cos theta 2 and 4 times v1 cos theta 1. And then vertically, there was no vertical momentum before. Afterwards, it's going to be 4 v1 sine theta 1 and 6 v2 sine theta 2. And then finally, if it is an elastic collision, then you would have the kinetic energy being conserved. Notice there is no issue about x or y here because kinetic energy doesn't have components, it's a scalar. But the point I finally wanted to make is that we have 1, 2, 3, 4 unknowns to solve for, and only 3 simultaneous equations. So it will not be possible to get a unique solution for this system. That if they were to tell you one thing, like both of these angles were the same, or they told you how fast this one was going, or what one of the angles was, then you would be down to just 3 unknowns, and you could do it with this system of 3 equations. But otherwise, you cannot do that problem. And that is all I have for you today.